I'm going to be talking today about surveying the epidemiology evidence, examples of triangulation from the IRIS program. And first, I'd like to acknowledge my co-authors on this work, Rebecca Nachman, Tom Bateson, and Elizabeth Radke-Faribault, all of whom work with me at the US EPA. So it's the same disclaimer I had before. The views expressed in this presentation are those of the authors and do not necessarily reflect the views or policies of the US Environmental Protection Agency. And this is going to be deja vu for just a couple of slides, but again, I'm going to provide some context for what I'm talking about by talking about the IRIS program. So EPA's Integrated Risk Information System, or IRIS program, develops and maintains a database of health effects information for hundreds of environmental pollutants. And we focus on toxicity that's due to chronic or lifetime exposure and provide numerical toxicity values for cancer and non-cancer effects. So again, IRIS assessments and documents are not in themselves regulatory documents, but they do contribute to regulatory decision-making, including cleanup levels and various legal acts, such as TSCA and Food Quality Protection Act and others, as shown on the slide here. So the screenshot here shows the front page of the ORD staff handbook for developing IRIS assessments. And this is exactly what it sounds like. We call it the IRIS handbook. And this describes the process that we use for developing assessment products, all the way from scoping and problem formulation. Chapter number 4 talks about study evaluation, how we conduct our risk of bias and sensitivity evaluations for animal studies and for human studies. Going all the way to step 6, which is evidence synthesis and integration, and closing with derivation of toxicity values. This handbook document is available online at the IRIS website, so epa.gov/IRIS if you wanted to look at this for more detail. And what I'll be talking about today, there we go. This is the same flow chart that I showed before, and it's very analogous to just reading down the table of contents for the IRIS handbook. But what I've circled here is evidence synthesis, which is the term that we use when we're looking at a single stream of evidence, so only animal studies, only human studies, and coming to a determination about what that single stream of evidence tells us before moving into evidence integration, where we draw those streams together. So with that backdrop, I'm going to move into talking about triangulation. So triangulation can mean many different things to different people, and the definition that I've put up here is consistent with some of the more recent publications from Deborah Lawler and other authors. And the definition here is the integration of results from different approaches taken to address a research question, where each approach involves a different source of bias, ideally not all in the same direction. So in the context of the IRIS program, we view triangulation as a strategy or a method or a tool that enables us to include and use as much information as possible when appropriate. And for our chemical health assessments, I showed that we had 2 different stages. We have evidence synthesis, where we're looking at one stream of evidence, and evidence integration across evidence streams. And really, for looking at integration across evidence streams, so drawing together the weight of evidence from animal, human, mechanistic, this is a more established approach, both in the IRIS program and other parts of the US EPA. But what is less formalized and less commonly referred to is when we're looking at the evidence synthesis stage, and we're trying to see how we can use triangulation, either looking at a single study or within a group of studies in a single stream of evidence. So I'd like to talk about a couple of examples of how we've used strategies that are in the spirit of triangulation in different IRIS assessments. So the first example comes from the Libby amphibole asbestos, or LAA, IRIS assessment. And in the tox review, we developed a inhalation unit risk, or IUR, which is the value that represents the upper bound on the excess lifetime cancer risk, estimated to result from a continuous exposure over a lifetime to 1 microgram per meter cubed in air. The data that were used to derive this IUR came from an occupational cohort study, and like many occupational studies, there was not complete smoking data available. Because the target outcome was lung cancer, there was concern that there could be uncontrolled confounding by smoking that could be biasing the effect estimate that was reported from the study. So in order to try and evaluate that potential for bias, we used a method that was published by David Richardson in 2010 to use a negative control outcome. So I'm sure that all of you are familiar with the concept of a negative control. Basically, you're looking at an association that you expect to be null. And if in your data set it is null, then that can lend confidence that what you're seeing is not being influenced so much by bias. But if it is not, then this could raise concern that something like uncontrolled confounding could be impacting your results. So I think we're all pretty familiar with thinking about negative control exposures because of things like randomized controlled trials. So the placebo arm would be your negative control exposure. And analogously, we can think about negative control outcomes. So we would want to look at an association where we don't expect to see that there's something going on between the confounder and a negative control outcome. So an example would be, for example, looking at cancer that is at a different and unrelated site compared to your cancer that is of primary interest. So in this little schematic here on the left-hand side, that kind of shows our starting situation. We want to know, is there an association between asbestos exposure and lung cancer, but we fear that smoking might be a confounder of that relationship. So rather than looking at lung cancer, instead we replace that with our negative control outcome, because we would choose an outcome that we think is related to smoking, our potential confounder, but is not related to the exposure of interest, asbestos. So for this analysis, we selected chronic obstructive pulmonary disease, or COPD, mortality, because we know that it is related to smoking, the potential confounder, but was not thought to be related to asbestos exposure. So in this case, when we're looking at asbestos in relation to COPD, we would expect that there would not be an association. And indeed, when we did that analysis, we didn't see that there was an association between those two. So this gave us more confidence that smoking was not an uncontrolled confounder in the asbestos and lung cancer relationship, because we saw what we expected to see, a null association, when we looked at asbestos and our negative control outcome. The second example I'd like to talk about that's in the spirit of triangulation is looking at the association between trichloroethylene, or TCE, and cancer. So I said that these are examples from the IRIS program, but I'm also going to be showing some screenshots of figures from the National Toxicology Program's report on carcinogens, as well as the IRIS toxicological review, just because the ROC is newer and had a few more studies and has some really nice forest plots that I wanted to highlight here. So this figure is showing showing a group of studies that looked at TCE and kidney cancer specifically, and they're arrayed by the level of exposure that was expected to be experienced by the study participants. So the top grouping of studies, these are situations where the study population was expected to have very high levels of exposure, so maybe an occupational setting where there was poor industrial hygiene or something. In the middle, we have studies where the levels of exposure were expected to be more moderate. And on the bottom, a grouping of studies where the level of exposure was expected to be relatively lower. And of course, this is not always true, but in many cases, if you have more of something harmful, you have more of the disease or more of the bad outcome. And you can see that expected pattern does seem to show up here, where the studies that had higher levels of exposure had higher relative risks compared to the studies that had lower levels of exposure. Now, this is showing the same set of studies, but rather than being arrayed by the level of exposure experienced by study participants, they're arrayed by the overall confidence rating for the study. So at the top, we have studies that were considered to be higher confidence. In other words, they had lower risk of bias ratings. In the middle is the moderate confidence studies. And then I thought this was very, very informative. We have groupings of studies that had lower or low moderate confidence, but they're separated by whether the bias is expected to be towards or away from the null. And when we have the studies arrayed in this way, we can see that the higher confidence studies had relative risks that were generally above the null, statistically significant. And if we look at those groupings of lower or low moderate confidence studies that had overall bias expected to be towards the null or away from the null, we do see that the pattern is as expected. So for example, those two studies on the bottom that had low confidence with overall bias towards a positive effect have extremely high relative risk estimates. So now I'm moving on to show the similar type of analysis that was done by the IRIS program for the 2011 TOX review. This is a forest plot, and a summary relative risk estimate from a meta-analysis. And I just want to point out that meta-analysis is not in itself triangulation. It's just a way of bringing together strength across studies. So we show that here. But more importantly, for thinking about triangulation, the talks review also had a very extensive discussion about potential heterogeneity among study findings, and could this be explained in an expected way. So one issue would be confounding by co-exposures, and whether that would influence both the study-specific and the overall or meta relative risk estimate. So in a lot of the occupational studies, we have folks with job titles such as a degreaser, and that could convey potential for co-exposure to things like mineral oils, hydrazine, and other solvents. So there's a discussion in the talks review about whether these co-exposures could be uncontrolled confounding that would be influencing the study and the overall risk estimates. So in the studies that were able to look at covariates, including some of these co-exposures, they did not find that the co-exposures were correlated with the exposure, so they wouldn't be a confounder for that reason, or they weren't associated with the outcome, kidney cancer, so they would, again, not be a confounder by virtue of not being associated with the outcome. So this type of discussion, which is much more lengthy and detailed than the actual talks review, led to the conclusion that potential co-exposure was unlikely to provide an alternative explanation for the association between the primary exposure, TCE, and kidney cancer. Other confounders that were thought to be potentially, that may have potential to bias the results were obesity or high body mass index, BMI, and smoking, because these are known risk factors for the outcome of kidney cancer. And again, there's a lengthy discussion in the talks review that kind of works through the logic of, do we expect to see that the bias would be acting across the entire group of studies or certain studies, or do we see any bias at all? And just some of the discussion points that I drew out here are that we had both cohort studies and case control studies in this grouping that were looking at TCE and kidney cancer. And for the cohort studies, just over half of them used internal controls. So it might be, for example, something like exposed workers in a factory and workers from the administrative department of that same factory. So the use of internal controls is generally thought to minimize potential confounding because the exposed and referenced are from a similar target population. In terms of the occupational cohort studies, there was evidence that obesity would be less of a concern because of the generally healthy nature of the employed population in those particular cohorts. And when looking differently at the case control studies, many of these actually did try to control for BMI or obesity, smoking, and other confounders, and did not find that these factors substantially changed their results. So I'll talk a little bit more about smoking on the next slide, but this type of thought process and grouping of studies allowed us to arrive at the conclusion that the association of TCE with kidney cancer was not being fully explained by uncontrolled confounding. So I mentioned that we looked at studies in different groupings, one of these being cohort studies versus case control studies. And in most cases, the cohort studies did not have information on smoking, while the case control studies did. However, when we look at the case control study relative risk from meta-analysis, just for case control studies, the relative risk was 1.48 compared to 1.16 for cohort studies. And it didn't seem that that the result was being driven by uncontrolled confounding by smoking that was not accounted for in those cohort studies. And a different strategy for trying to get at this potential for confounding by smoking was to look at lung cancer. So again, the cancer of interest for this particular question is kidney cancer, but you might expect that if TCE is associated with smoking, and that is kind of driving the association with kidney cancer, then TCE would act similarly to smoking for lung cancer as well, which is, again, a known association between smoking and lung cancer. However, that wasn't the case. We saw that the relative risk for lung cancer was actually close to the null and not significant, so this gave us more confidence that smoking, again, was not driving that association. So I think I'm running a bit over, but just in summary, we wanted to show a couple of examples from the IRIS program of how we've used strategies or methods in the spirit of triangulation to look at a causal association between an exposure and a health outcome, with the goal of including and using as much information as we can across the body of evidence. Thank you.